Hi there. I had to be gone today, so here I am trying to be here when I'm not here. I'm going to go as quickly as I can through this. Feel free that if I'm going too fast for you to be able to write down what you need to write down, that you just pause it and then start playing again. But by now, ideally, you have your progress report, and of course get that signed, any late work attached to it, all the normal rules apply. You have seen your silly song by now, and now you're ready to go. You should have a note sheet in front of you, and on the back of that will be your assignment sheet. So if you have your note sheet in front of you, we are ready to go. Today we're going to talk about projectiles, and projectiles are our new unit, and we get to learn about projectiles. You'll like it a lot. A projectile is anything that flies through the air, influenced only by three things. The three things we influence are inertia, gravity, and air resistance. Of course, inertia tells us that we want to keep doing what we've been doing. Gravity tells us that we want to accelerate that way. And air resistance says we're going to slow down. Air resistance we get to ignore, which only affects objects that are either extremely light or traveling at extremely high velocities, and we're not going to be throwing pieces of paper around. We're not going to be throwing around bullets. So this should work out just fine. If the object is self-powered, it is not a projectile. If it flies like a rocket, it is a projectile. So basically the two rules that you want to think of in judging is this a projectile or not is if it's self-powered, it's not a projectile. So airplanes, no. Rockets, no. Birds, no. These won't work unless we shoot the bird. Then the bird becomes a projectile afterwards. So self-powered, not a projectile. Basically, if you chunk a rock through the air and you notice the way it flies, that's the way a projectile flies. So if it flies like a rock, then it is a projectile. So we can ask, which of these is a projectile? Well, if we chunk a cheerleader up in the air, is she going to be a projectile? Yes, she's not self-powered. She doesn't have rockets attached to her. She's not magic, so that's going to be worked out great. If we throw a football through the air, same thing. A football flies just like a rock. It's going to travel just fine. If we throw Larry Boy through the air, Larry Boy, that's when Larry puts on his spandex superhero outfit, and he doesn't have any magic power, so yes, he flies like that. Now when we get to a frisbee does not fly like a rock. I can make a frisbee curve around, I can make a frisbee come and go up slowly and then come down slowly. I can't do that with a rock, so the frisbee is not a projectile. If I throw a paper airplane, if you make a really, really bad paper airplane, then it probably would be a projectile, but most paper airplanes are not. In fact, I can make a paper airplane that loops the loop and flies around in circles. You can't do that with a rock, so that is not one. A water balloon, on the other hand, flies just like a rock does. So if you're shooting water balloons around town, that will travel in parabolic motion, so we'll like that. A bottle rocket would not be a projectile because a bottle rocket is self-powered. So you let go of the fuse and it shoots up in the air. If we're talking about fireworks, once they explode, then the little bits look like parabolic trajectories, so they are in fact projectiles. A curveball, if I throw a curveball when I'm in baseball, when I throw a curveball I put a spin on the ball and the ball ends up curving, which we don't see rocks doing again. So the curveball, the frisbee, and the paper airplane, they're not self-powered the way the bottle rocket was, but they're still not flying like a rock does. And if they're not flying like a rock does, then that tells me something else is involved. I don't have to understand what the something else is to know that it's not a projectile. So all projectiles are going to travel the same way through the air, and the path this projectile takes is called its trajectory. So the trajectory is the path it takes through the air. So if I throw you off the roof of the building, that path that you fall through the air is going to be your trajectory. Now, every true projectile is going to have a shape of a trajectory that makes a parabola. So all projectiles are going to travel in parabolic trajectories. So again, if it's not a true projectile, it's not going to be a parabola. If you don't see a parabola, it's not a true blah, blah, blah. Why do we get a parabola? Well, we get a parabola because we actually have two different types of motion happening at the same time. We have horizontal motion and we have vertical motion, and they're not the same type of motion. Horizontal motion is controlled only by inertia, and inertia says we're going to travel at a constant speed in a straight line. The vertical motion, on the other hand, is affected by gravity. So the horizontal motion, being affected by inertia, can only travel at a constant speed. The vertical motion being affected by gravity, which is an acceleration, is going to always be an acceleration. So the good news is we can pretend like the sideways trip is happening independently of the up and down trip, and it makes the math a whole lot easier, and we can get away with taking what is complicated motion and breaking it into two simple type of motions that just happen to be happening at the same time. So you'll like this because it turns out to be pretty easy. Now the formulas we're going to use. Horizontal motion is constant speed motion. There is only one constant speed formula, and that was V equals d over t. So if we bring the t up, we get this. Where do the little h's come from? Well, the h's stand for horizontal. So those are just reminders that, hey, we can only plug in distances and velocities that are going this way when we use this formula. So vertical motion is an acceleration, so we can get away with any of our acceleration formulas that we learned in Unit 2, but the one that we're going to use most often is going to be this one. So the d equals at squared over 2 plus vit was the way it originally looked. We changed the a to g, because g is always negative 9.81, and it has to be negative there. The vvi is the initial vertical velocity, so this is how fast I'm going straight up and down. So don't put in a velocity that's going sideways here, that would be bad. And this v also stands for vertical, so this is a displacement up and down. So this tells me how high up and down I am. Now since this is displacement and not distance, then it does have a direction. So if I plug into this equation and I get a positive number, it means I am higher than my launch position. If I plug into this equation and get a negative number, it means I am lower than when I started. So that direction does make a difference. So that's the one that we're going to use most often, and the one that we're going to use today. Now, here's today's trick. It's not very hard. These are equations we've used before. You know how to use this kind of stuff. You'll have it made. The one thing in common between the two formulas is time. So the whole time I'm going sideways, I was also going up and down. The whole time I'm going up and down, I'm also going sideways. Which means I can solve this equation for t and shove that t in here, or I can take this equation and solve it for t and shove that t up there. So that's what we're going to do today. This is going to be simple two-step problems, one here that shoves into here, or one here that shoves into there. So we will like this a lot. Here we have Vivi throwing a tennis ball sideways off a building with a 13.2 meters per second velocity. If the building is 4.57 meters tall, how far to the side does the ball hit? Well, of course, one of the ways it's easier to do this is if you kind of draw a picture. We've got Vivi on top of the roof, so here she is on top of the roof, and she's got her tennis ball in her hand. She's going to throw it sideways. So she's going to throw the ball this way with the 13.2 meters per second. And again, when we see meters per second, we think velocity, and that's great. We would still think velocity. We're not going to worry so much about initial and final in this unit. What we're going to worry about is this velocity going sideways, or is this velocity going up and down? So in this case, we're going sideways, so that is horizontal. So this is going to be my VH. Next, I say, is the building 4.57 meters tall? So 4.57 meters was how tall the building is. So if I'm going up and down here, that's obviously, since it's meters, that's going to be a duh. But which direction we're going? So again, the key in this unit, am I going side to side? I stick an H on it. If I'm going up and down, I stick a V on it. So this is going to be dV. So now I'm looking for how far to the side does the ball hit. Well, how far, of course, is looking for a D. How far to the side is looking for DH. So I'm looking for DH. So if I'm looking for DH, again, we have our two equations that we wrote down a second ago. And we have DH is equal to VH times T. I already know my VH is 13.2. The thing I don't know is my time. So I say to myself, how can I find time? I don't have anything here to find time with. I do have something to find time with. It's this one. So we take our second equation. Our second equation says dV equals gt squared over 2 plus dvit. Now, the initial vertical velocity, initially we were only going horizontally. We were not going up or down either way. So this is going to be 0. If this is 0, then this whole thing crosses off. And in today's assignment, this will always cross off. Friday, we'll learn what happens when it doesn't cross off, but for today, this one will always cross off. So if I'm looking for t, it becomes easy. The 2 comes from the bottom up to the top. The g goes from the top on this side to the bottom over there. To get rid of the square, we need to square root. So if we want to make this not ugly, this will give me my time. Now this formula only works when I'm falling down from an initial velocity of 0. Because again, that VI we crossed out as t. So it has to be from the highest point down, which is this doing. This is just going to fall down. So of course it'll fall in a nice parabolic trajectory. And so that's going to be the time. This is what we're going to call this is the time down equation. So this calculation only works for how far we're falling down. And the only d I can stick in here is a d going down. Never try and stick a sideways d in this equation or it'll totally mess you up. This only works down. So if we plug this in, of course, we have 2. And the d I'm falling down is 4.57 meters, but I'm going to put negative 4.57 meters because the negative means I'm falling down. And then we divide that by g. And g, of course, is negative 9.81. And we square root that. And of course, this negative and that negative will cancel, which is a good thing, because if I try and take the square root of a negative number, my calculator screams at me. So if I open this up and I say second square root, parentheses opens up, I want to do this inside the parentheses. So 2 times negative 4.57 divided by negative 9.81, close it, equals, and I get 0.965 seconds. So what was I missing up here? I was missing the time. This was how much time it took to fall down. The whole time it was falling down, it was also traveling sideways. So this time goes right there. So if I just multiply that times the 13.2, I say, hey, that was 12.7 meters over is how far the ball went in the time it took it to fall down to the ground. So again, that was really easy. I just plug into the time when I'm falling down, and then I take that time and I shove it into the other equation and see how far sideways I'm going. So far, really, really easy. We like that. Next. Here we have Jessica talking on her cell phone while she's driving 24.5 meters per second. She misses a turn, careens off a cliff, and falls in a parabolic trajectory until her car explodes into a fireball 146 meters from the base of the cliff. How tall was the cliff? No moral to the story here. Quit texting while you're driving. Quit driving when you're talking. Concentrate on driving so you stay alive or something. So here was Jessica driving her little bubble mobile. And as she's driving along on the car, she's driving 24.5 meters per second. So again, when I see meters per second, the first thing I should think of is velocity. The second thing I should think of is, am I going this way or am I going this way? And in this case, clearly cars can only drive horizontally. You don't see those driving vertically too often. So we have 24.5 meters per second is our horizontal velocity. And then the next number we see is 146 meters from the base of the cliff. Of course, she's going to fall in a nice parabolic trajectory until she hits the bottom and explodes in a nice fireball. And the fireball happens 146 from the base of the cliff. So that means from here to here was 146 meters. Well, again, meters is always going to be d. And this time I have to say which d. Well, d going this way is going to be dh. So I have a dh and I have a vh, but I'm looking for how tall was the cliff. So I'm looking for how tall is the cliff. Well, of course, if I'm looking up and down now, I'm looking for dv. So I want to know what is my dv. Again, dv, I have one nice dv equation that I like to use, and that's going to be the gt squared over 2 plus dvit. But again, in today's assignment, that's always going to cross off. So we're going to drop that. I know g is negative 9.81. I know that t is, I don't know. So I got it made as long as I can find a t. But then I say to myself, how do I find the t? Well, I know VH. I know DH. Hey, I know that I have a formula that says VH equals VHT. So if I know these two, I better be able to solve for that. So if the t is here, then the the t stays here, the VH wants to move underneath. That's the way we algebra. So the DH is going to be on top, VH is going to be on the bottom. So we'll have 146 divided by the VH of 24.5. When we plug into that, 146 divided by 24.5 equals, and I get a beautiful 5.96 seconds, which means Jessica got to scream into her phone for 5.96 seconds before it suddenly went dead. And so, of course, this is the time that's going to go right there. So that will get squeak times negative 9.81 divided by 2 gives me a beautiful answer of negative 174 meters. Now, of course, this negative is, again, displacement. So what this is saying is when she comes off the cliff, she ends up 174 meters lower than when she started. I didn't ask how far she fell, though. I asked how high she was in the first place. So you wouldn't write negative 174. That would sound weird. So the cliff was 174 meters tall. So that would be how you solve that type of problem. Which, again, this becomes a quite simple problem. All we've got to do is always 2 steps. So for homework, of course, we're starting a new unit, and you think you're going to want problems A, but you're going to want problems 1 this time. We're going to chop it into 1 and 2. But again, all we have to do is think about our 2 equations. We had 2 equations. One was dH equals VH times T, and one of them was dV equals GT squared over 2 plus VVIT. Again, in today's assignment, this will always go away. And so really, I only care about the first half of this. But when I solve this one for t, the VH comes down. So I'm going to have dH over VH equals t. And when I'm solving this one for time, this part drops off, this comes up, this comes down, and we end up with our t down equation is equal to 2dV over g. So if I give you how far up and down it is, I can find out how far down it falls, and I can use this time and shove it in there. If I give you both dH and VH, then you can find the time, and you can take this time and shove it in there. This is going to be the trick. Sometimes I shove this into here and I solve for dH. Sometimes I shove this into here and I'm solving for VH, so I move the t underneath. Sometimes I give you these two and you can solve for time, and you put it in here and you find out how high you are. That's all there is to it. 2 easy steps. One from this side goes into there, one from that side goes into here. Everybody can handle this. Everybody can have 100% success. And so I want all this done. Problems 1, ready to go for tomorrow. So be good, work in your groups. You know what to do. Make me proud. See you tomorrow.